Let us study the setup of basic flow and energy models now. The flow and energy models are nothing but computational representation of the Navier-Stokes equations. We all know that CFD is numerical solution of Navier-Stokes equations. Hence, in CCM Plus also, the flow and energy models are numerical algorithms which solve Navier-Stokes equations. Let us review the Navier-Stokes equations before we go into depth of model setup. All of fluid dynamics is based on three physical principles. Mass is conserved, Newton's second law, and energy is conserved. These physical principles are developed into the fundamental governing equations of fluid dynamics: the continuity, momentum, and energy equations. These equations are also known as transport equations or conservation equations. The form of governing equations that is generally used in computational fluid dynamics, CFD, is known as the Navier-Stokes equations. The Navier-Stokes equations include the effect of viscosity on the fluid flow. In CCM Plus, the finite volume method is used to transform the continuous governing equations into a form that can be solved numerically. Two approaches are taken to solve the governing equations. First is the segregated approach, where the flow equations are solved one after the other and linked using a correction equation. Other is the coupled approach, where the coupled system of equations is solved simultaneously. We said that for CFD, the continuum mechanics formulation should be valid. So how to know whether the continuum mechanics formulation is valid or not? The Knudsen number Kn determines whether the continuum mechanics formulation of fluid dynamics is valid. The Knudsen number is defined as the ratio of molecular mean free path to the characteristic length of the body. For high Reynolds number, the Knudsen number is given by other formulation as shown. In this formula, m is the Mach number, gamma is the ratio of specific heats, and the Reynolds number Re is dependent on L. Flow problems can be divided into four general regimes that are based on the Knudsen number as shown. When Knudsen number is less than 0.01, we call the flow regime is under continuum. When Knudsen number is between 0.01 and 0.1, we say it is slip flow. When Knudsen number is between 0.1 and 3, the flow is transitional. And when the Knudsen number is greater than 3, there is free molecular flow. CCM Plus can be used in the continuum regime where the Navier-Stokes equations are valid. In the slip flow regime, the Navier-Stokes equations can produce good results. However, the effects of rarefaction must be taken into account through slip velocity boundary conditions and accounting for temperature jump on the surface. Solving for transitional flows requires a statistical method such as a direct simulation Monte Carlo approach. In the free molecular regime, the flow is sufficiently rarefied that molecular collisions can be neglected. The continuum assumption that is built into the Navier-Stokes equations is not applicable to these rarefied gas regimes. How to model high-speed flows? In high-speed flows or at high Mach numbers, extreme temperatures occur and dissociation or even ionization of the gas must be considered. Basic changes in models depend on density and specific heat variations or loss. The match number regimes and the appropriate models to use vary by gas and upstream temperature and pressure. When match number is less than 3, the flow regime is calorically perfect and we can model the flow using ideal gas equation and constant specific heat. When match number is between 3 and 8, the flow regime is thermally perfect, and here also we can use the ideal gas equations but with specific heat, a polynomial function in T. For match number greater than 8 and less than 30, there is dissociation. For this, we need to use real gas model or consider chemically reacting flows. For match number greater than 30, ionization occurs. This requires solving the Navier-Stokes equations together with the Maxwell equations. This is not currently possible in star CCM+. Star CCM+ simulates various pressure quantities depending on the model selection. Let us understand these different pressure types before we start learning how to set up simulation. This is important because you need to know the meaning of all these different pressure types in order to decide your model setup inputs. First is the reference pressure. This quantity is a value that reduces the numerical round-off error in the numerical calculations involving pressure. Then we have the working pressure. This is the solution variable that is used in the flow models in star CCM+. In the software, this is mentioned as simply pressure. Its definition is a matter of computational convenience and depends on the model selection. It is always expressed relative to the reference pressure. In laminar flows without the influence of gravity, pressure is equal to the static gauge pressure. If the gravity model is active, pressure is equal to the piezometric pressure. Then we have the static pressure. This is the spherical part of the stress tensor acting in fluids. The static pressure is the same as the thermodynamic pressure, which is one of the static variables. Next is the absolute pressure. This is the sum of the static pressure and the reference pressure. After this, we have relative total pressure. This is the static pressure that results from isentropically bringing the flow to rest in the relative frame of motion. Next is the total pressure, which is the static pressure that results from isentropically bringing the flow to rest. Finally, there is the absolute total pressure, which is the sum of the total pressure and the reference pressure. So this was all about different pressure types. Now let us see how to input some of these values.